Okay, let's do some graphing on Desmos here to try to get to the idea of what's going on here in the most general case. I've taken the case where we had in a previous video, y equals x divided by x plus 3 times x minus 2. And we graphed that, and we found there's vertical asymptotes at x equals negative 3 and at x equals 2 as shown. Okay, now that's actually in blue for the moment here. Let me take this off for a second here. Okay. Alrighty. All right, that's our original graph. There was no great mysteries there. What we were concerned with was what? Finding, in doing this and graphing this, we were interested in where the graph crossed the horizontal asymptote, right? Okay. Now, in general, or where it bounced, how it interacted with the horizontal asymptote. That's the same idea we're going to do in general, but it's going to be interacting with what? It's going to be acting like the general polynomial asymptote that we're calling q of x, okay? And I'm trying to give you the idea of what goes on in the long run here, and hopefully this picture will help you. Okay, so this was our original, no big deal here. Now I'm going to come down over here and I'm going to introduce, now take a look over on the left-hand side, okay? I'm going to put this in here. I've got y equals mx plus b plus x over x plus 3 times x minus 2. So we have the same r of x over d of x that we had before, but this time I'm sticking in what? A q of x, which is mx plus b. Now at the moment, this is identical to the one above because m and b are both 0, as you can see right here, okay? These are both 0 right here. Now I'm going to go ahead and click this guy off here, since we have the idea. And then what I'm going to introduce, I'm going to start introducing a non-zero value of b and start thinking about what this actually ends up looking like. Okay? Okay, I took a value of m here, which is 0.2. That's a fifth. That's fairly small. Do you notice that it's not asymptotic to the x-axis anymore. It's asymptotic to some line. Well, what line do I claim it's asymptotic to? Well, come up here. Do you remember I say it's always asymptotic to the q? What is the q this time? It's mx plus b with m is equal to 0.2, right? So I'm going to come over here and do this. I'll click on mx. Since b is 0, those should be identical. Okay, in fact, I'm going to put in here plus b, because b is still 0. Do you see the mx plus b? Hey, in the long run, look at this thing. It's acting just like that line, y equals mx plus b. That's what I mean about it being what? Asymptotic as x approaches plus or minus infinity. But notice here, the graphs, this is almost like the previous example where m is equal to 0. It's crossing the asymptote, the horizontal, the oblique asymptote is what it should be called this time, instead of the horizontal asymptote, but it's having the same type of behavior, right? Do you see what I mean? It's like I took the previous graph and just sort of, tilted it. By the way, I could also put a b in here. Oops, that's sort of an animated b. I don't want to do that. Okay, that's kind of extreme. But you see there, I've got a vertical shift here. Once again, it's still asymptotic. Yeah, maybe I will animate it. It's still asymptotic. See? It's acting like the q of x, isn't it, in the long run? Okay? All right, let's stop this. Let's play with the m a little bit. This is going to be kind of extreme here. Watch this. Okay? But you still get the idea that it's what? All right, let's stop this. Let's come back and take this off here for a second. Okay? Remember the original? It was what? Below the asymptote here, the horizontal asymptote. I'll call that the polynomial asymptote because that's in general, right? It's below the polynomial asymptote, then it's above, crosses, then goes below, and then it does what? It's above here. Get this red one off too. Okay? All right, got it? All right. That same behavior is still occurring here in the case where I let, here, let's animate both of these. This is crazy. Okay. There you see? Still above. See? It's still up, I should say below, above, crosses below, then it's above, right? Okay? Just like that situation, okay? All right. Now let's play around with this a little bit more here. There I've taken oblique asymptote. Let's get rid of all this, okay? Still have the same vertical asymptotes though, right? We still have those problems where the denominator, when it goes to 0, that you run into a little bit of difficulty there, right? Let's try a quadratic one just real simply. Okay. Here, maybe I'll put an a in there. Okay. X divided by x plus 3, x minus 2. Alrighty. Probably should have had that up there. What would this be asymptotic to in the long run, right? Yeah, y equals a x squared. Okay, I'm going to add my slider. It has a default slider here being 1. This is the default value on the slider, I should say. Okay, now suppose a is 0. If a is 0, my q of x here sitting out front, let's put that back in parentheses here, is the same as what? 0. It's 0, so it's the same situation as I'm dealing with in my original here. Okay? But I'm going to pick that ax squared off. Now I'm going to animate this a little bit. Let's go ahead and see what happens. Okay? Let's zoom in too. Okay? Let's pull this off. There we go. Okay. Notice it's the same general shape though. Okay. This is what? This is my asymptote. This is my parabola. Okay. Again, the distance between the actual function and the parabola, right, the polynomial asymptote, goes to 0 as x approaches plus or minus infinity. So if I zoom way out, you know, it's looking like what? Except for that screwy stuff in the middle, it's looking like the quadratic, right? Okay, definitely screwy stuff on the inside here, though. Okay, but do you see it had this same general idea, right? It's what? It's still approaching the asymptote from below here, and then what? Approaching the vertical asymptote like that, going below. Then what? Above, crosses, below, and then stays above here like that. Okay? So let's animate this. Crazy stuff, huh? Okay? I hope you guys get the idea that you can have something other than a linear asymptote. A lot of teachers don't do the quadratic or higher degree asymptotes here. Okay, I'll do one last one just to show you here. Let's go to the third power. Okay, let's go 3. Now I have ax cubed. Okay, let's make the a much smaller here. And let's zoom in. All right, let's zoom in here. Remember how the cubic looks? Okay. Okay. I hope this helps you get an idea of what's going on here. Okay. I'm not sure it does, but I'm trying my best here. Okay. Well, there it is. One last thing I'll comment about is the irreducible quadratic factors, but I'll do that in a minute. Okay, I just wanted to show real quickly what happens when you add factors for irreducible quadratics. Okay, what does that do to the graph here? Let's come over here. Let me take this off here for a minute. Here we've got our original here, y equals x divided by x plus 3 times x minus 2, the same one we've been looking at here. X squared plus 2x plus 2 is an irreducible quadratic because if you set it to 0 and use the quadratic formula, you're going to find that you get imaginary zeros. What does this end up doing to our graph, these little quadratic factors? All it ends up doing is creating a little wrinkle here. Okay, so they can give us some local max and mins that might not otherwise exist, but other than that, they're really not going to affect the graph that much. Here, compare this. All right, there's the one with the factor x squared plus 2x plus 2. There's the original. See the difference between the two? Not really all that much, right? X squared plus 2x plus 2 has a single sign, right? It's always going to be positive for all real values of x. If it wasn't, it would have some real zeros, okay, which it doesn't. So that's why we're not going to worry about too many of these, but we've spent enough time on this already as it is. So there you go. That's the end of rational functions.